Instruction format defines, first a computer performs a task based on the instruction provided, and it defines the different component of an instruction. Main components of an instruction are opcode, which instruction to be executed, and operands, the data on which instruction to be executed. Here are the different terms related to the instruction format. As we can see on the screen, instruction set size, it tells the total number of instructions defined in the processor, and opcode size, it is the number of bits occupied by the opcode, which is calculated by taking log of instruction set size. And then next, operand size, it is the number of bits occupied by the operand. And then last, instruction size, it is calculated as sum of bits occupied by opcode and operands. Now let's solve the problem on type 1. In this type of questions, you will be given the size of instruction set, number of operands and their size, which is a count. You have to find out the size of the instruction. Let's see the question 1. Consider a processor with 64 registers and an instruction set of size 12. Each instruction has 5 distinct fields, namely opcode, 2 source register identifiers, 1 destination register identifier. So after combining all these fields, we will get 5 distinct fields and a 12-bit immediate value. Each instruction must be stored in a memory in a byte aligned fashion. That means we have to store in a byte format. If a program has 100 instructions, the amount of memory which should be in bytes consumed by the program text is how many bits? So we have options here. Option A 100, option B 200, option C 400, and option D will be 500. Do anyone have idea or any guess about the question? Anyone? Okay, let's see the solution so that you will understand more clearly. So here is the solution. Let's discuss the solution now. The instruction consists of opcode and operands. Given the instruction set of size is 12, as we all know, here in the fourth line, 12-bit immediate value. So instruction set of size is 12. 4 bits are required for opcode. As there are total 64 registers, 6 bits are required for identifying a register. Now, as the instruction contains 3 registers, that is 2 source plus 1 destination, and 3 into 6 is equals to 18 bits are required for register identifiers. As given in the question, we all know 12 bits are required for immediate value. So total bits for an instruction will be 34 bits. That is 4 plus 18 plus 12 plus. If we add all these 3, we will get 34 bits. Hence, for 100 instructions, number of bits will be 425 bytes. That is 34 into 100 is equals to 3400 bytes. Then divide the value, which is 3400 by 8 bytes, and you will get 425 bytes. Since we all know 1 byte is equals to 8 bits. Then therefore, as you all know that memory must be greater than or equals to 425. So choose the correct value which is optimal to the condition. Hence, correct option is D, 500, which is equals to 425 or greater than 425. And now let's see the type 2 question solving. In this type of questions, you will be given the size of instruction, size of opcode, number of operands, and size of some operands. You have to find the size or a maximum value of remaining operands. So now let's see the question 2. A processor has 40 distinct instructions and 24 general purpose registers. A 32-bit instruction word has an opcode, 2 register operands, and an immediate operand. The number of bits available for the immediate operand field is. So we have to find the answer. I think we don't have options here, and even I don't want to confuse you to the core. So let's give you 2 options such that you can select any one of the option. Option A 32 bits, option B 16 bits. So do anyone have any idea or guess about this type of question? Or okay, now may I hear the option from you? It's okay to guess because we will learn more about it later. Okay, let's see the solution in next slide. As the processor has 40 instructions, number of bits for opcode will be 6. This is 64-bit register. Next, as the processor has 24 register, number of bits for one register is 5. This is 32-bit. Total bits occupied by opcode and two registers is 16, which is 6 plus 5 plus 5. As instruction size given is 32 bits, remaining bit left for operand is 16 bits, which is 32 minus 16. So the option is B. Option is B, 16 bits. I hope you understand this question. Anyone have a doubt in this solution? Anyone? Okay, let's move on to the next slide. Let's see one more question in type 2 so that you will be more clear on solving. Question 3. A machine has a 32-bit architecture with one word long instructions. It has 64 registers, each of which is 32 bits long. It needs to support 45 instructions which have an immediate operand in addition to two register operands. Assuming that the immediate operand is an unassigned integer, the maximum value of the immediate operand is. So we have to find the answer for this. So this question is from GATE CS 2014 question. I think we don't have options for this question also. It's okay, no problem. Let's solve the problem without options. This is the solution here. As machine has 32-bit architecture, therefore one word is equals to 32 bits, which is an instruction size. As the processor has 64 register, this is directly from the question. As the processor has 64 register, number of bits for one register is 6 and is of 64 architecture, 64-bit architecture. As the processor has 45 instructions, number of bits for opcode is 6 and is of 64-bit architecture. So total bits occupied by two registers and opcode will be 18. As 6 plus 6 plus 6 is 18. As instruction size given is 32 bits, remaining bit left for immediate operand is 14 bits. As 32 minus 18 is 14 bits, we know that. Maximum assigned value using 14 bits is 16,383, which is the answer. We will get by 2 power 14 minus 1. So understand? Let's move on to the next slide. Here we have a type 3 question and let's see how it solves. In this type of questions, you will be given different categories of instructions. You have to find maximum possible instructions of a given time. So here is the question. Question is, a processor has 16-bit registers, that is R0 and R0, R1 or up to R15, and 64 floating point registers F0, F1 until F63. It uses a 2-byte instruction format. There are 4 categories of instructions. Those are type 1, type 2, type 3 and type 4. Type 1 category consists of 4 instructions, each with 3 register operands, that is 3 R's. Type 2 category consists of 8 instructions, each with 2 floating point register operands, 2 F's. Type 3 category consists of 14 instructions, each with 1 integer register operand and 1 floating point register operand, 1 R plus 1 F. Now, type 4 category consists of n instructions, each with a floating point register operand 1 F. The maximum value of n is. We should find the answer for this question. It will be a confusing question, but you have to note all the types in point wise so that you will be more clear. This question came on 2018 for GATE. So the options are 64 and 32. Do anybody know the answer for this type of question? It's okay to guess. Okay, let's move on to the solution. So here is the solution. As machine has 2 byte, that is 16 bits instruction format. Therefore, possible encodings are 2 power 16. As the processor has 16 integer register, number of bits for one integer register is 4. As the processor has 64 floating point register, number of bits for one floating point register is 6. For type 1 category, having 4 instructions, each having 3 integer register operands, will consume 4 into 2 power 12, that is equals to 2 power 14 encodings. For type 2 category, having 8 instructions, each having 2 floating point register operands, 6 into 2, that is equals to 12 bits, will consume 8 into 12 power 12, that is equals to 12 power 15 encodings. For type 3 category, having 14 instructions, each having one integer register and one floating point register operands, that is 10 bits. 4 plus 6 will be 10 bits. Will consume 4 into 2 power 10, that is equals to 14,336 encodings. And now coming to the next, for type 4 category instructions, number of encodings left is 2048. That is 2 power 16 minus 2 power 14 minus 2 power 15 minus 14,336. So which we got in type 3 category. For type 4 category, having n instructions, each having one floating point register operand says 6 bits will consume n into 2 power 6, that is 2048. Calculated from previous step, we know that 2048 is the previous step answer. Therefore, n is equals to 32. So answer is 32. Do you understand how to solve the problems on instruction format types of question? Having any doubt? Anyone have any doubt? Hope you understand clearly, and let's move on to the next slide as you have no doubts. So addressing modes. Operand can be either in one of the processor register or in memory. There are different ways to get the operands. The way in which the operand is taken from register or memory is named as addressing mode. The term addressing modes refers to the way in which operand of an instruction is specified, and it specifies a rule for interpreting or modifying the address fields of instruction before the operand is actually executed. So next, let's move on to the next slide. Here we have types of addressing modes, and let's discuss the types of addressing modes one by one. So first one is register addressing mode, second one is absolute or direct addressing mode, third one is immediate addressing mode, fourth one is indirect addressing mode, fifth one is index addressing mode, sixth one is relative addressing mode, seventh one is auto increment addressing mode, eighth one is auto decrement addressing mode. And first one, let's discuss the first one, register addressing mode. The operand is specified within one of the processor register. Instruction specifies the register in which the operand is stored. The operand is the contents of a processor register. The name or address of the register is given in the instruction. It is used to access the variables in the program. For example, move R1, R2. So the instruction copies the content of R1 into the R2. Hope you understand this register addressing mode. So now absolute or direct addressing mode. We call absolute addressing mode, or we can also call direct addressing mode. The instruction specifies the direct address of the operand and the memory address is specified where the actual operand is. So the operand is in the memory location. It is also used to access the variables in the program. For example, move A, 2000. This instruction copies the content of the memory location A into the memory location of 2000. Hope you understand. Instructions are very easy in this modes. So the only thing is that you have to understand the instruction. Immediate addressing mode. Now, in this mode, data is present in address fields of instruction, designed like one address in instruction format. Note that the limitation in the immediate mode is that the range of constants are restricted by size of address field. Addresses and data concepts can be represented in assembly language using the intermediate mode. The operand is given explicitly in the instruction. For example, move hash 200 comma r0. Here hash is the front of the value to indicate that this value is to be used as an immediate operand. For example, we have a is equals to b plus 6. Now we are adding hash 6 comma b. Now we are moving b comma a. We are moving contents of b into the a. As I told you earlier, the thing is that we have to understand and it will be very easy. Instructions are very easy here. Now, indirect addressing mode. In this mode, the instruction specifies the indirect addresses where the effective addresses of the operand is placed. The memory address is specified where the actual address of operand is placed. In this mode, the instruction does not give the operand or its address explicitly. Instead, it provides information from which the memory address of the operand can be determined. We refer this address as the effective address. We shortly call as EA of the operand. The effective address of the operand is the contents of a register or memory location whose address appears in the instruction. In this direct addressing mode, address fields of instruction contains the address of effective addresses. Here, two references are required. First reference to get effective address. Second reference to access the data. Now, based on the availability of effective address, indirect mode is of two kinds. A register indirect and memory indirect. Register indirect mode, in this mode, effective address is in the register and corresponding register name will be maintained in the address field of an instruction. Here, one register reference, one memory reference is required to access the data. And then next, memory indirect. In this mode, effective address is in the memory and corresponding memory address will be maintained in the address field of an instruction. Here, two memory references required to access the data. Hope you understand this indirect addressing mode. Anyone have any doubt in this indirect addressing mode? So no doubt. Let's move on to the next slide. Here we have the example of indirect addressing mode. To execute the add instruction, the processor uses the value B, which is in register R1 as the effective address of the operand. It requires a read operation from the memory to read the contents of the location B. The value then the value read in the desired operand, which is a processor, adds to the contents of register or not. Indirection through memory location is also possible, as we can see in the example. And we have the expression called EA is equals to X plus RI. X is constant value, which is an offset or displacement. RI is the name of the register, basically, which is a memory location. So hope you understand this example. Let's move on to the next slide. Index addressing mode. In index addressing mode, Contents of index register is added to address part of instruction to obtain effective address. The address part of instruction holds the beginning or base address and is called a base. The index register holds the index value, which is a positive. Base remains same, but the index changes. The effective address of the operand is generated by adding a constant value to the contents of the register. This mode is symbolically represented as x of Ri, where x is the constant value contained in the instruction and Ri is the name of the register. The effective address of the operand is given by EA is equals to x plus Ri. We already have seen the example on this equation before. The index register Ri contains the address of a memory location, and the value of x defines an offset, also called as a displacement, from this address to the location where the operand is found. So let's move on to the next slide. This is the example of the offset. Offset is given as a constant and offset is in the index register. We have two offsets as a constant and in the index register. Here first example in constant is add 20 of R1 comma R2. So we are adding 20 to the R1. So they taking 1000, we are adding 1000 to the R1, and to the in the index register example as given as add 1000 R1 comma R2. We are adding 20 to the R1. So here we can see on the left side we can see the 20 is equals to offset, and the here also in constant offset we can see 20 is equals to offset. We are adding the variables to the R1 till the operand. And let's move on to the next slide. Relative addressing mode. Relative addressing is the technique, it is a technique of addressing instructions and data areas by designating their location in relation to the location counter or to some symbolic location. This type of addressing is always in bytes. It never be in bits, words or instructions. Remember that it is always will be in bytes, never be in bits, words or instructions. In relative addressing mode, contents of program counter is added to address parts of instruction to obtain effective address. The address parts of the instruction is called an offset, and it can be positive or negative. When the offset is added to the program counter, the resultant number is the memory location where the operand will be placed. A useful version of this mode is obtained if the program counter is used instead of a general register. Then x of program counter is used to address a memory location that is x bytes away from the location presently pointed by the program counter. Actually, its common use is to specify the target address in branch instructions. For example, we take branch is greater than 0 loop. Process execution to go to the branch target location identified by the same name loop if the branch condition is satisfied. This location can be computed by specifying it is an offset from the current value of the program counter. Hope you understand this relative addressing mode. And I wanted to remind you that this type of addressing is always will be in bytes, never be in bits, words or instructions. So next one, auto. No, before that, let us see this branch, how this works. Branch is greater than or equals to loop. So it is in the format of looping. So the branch, so looping again and loop till the program counter satisfied, or target address in the branch instructions. So it specifies the target address in branch instructions till the loop satisfies. So auto increment addressing mode. Effective address of the operand is the contents of a register specified in the instruction. After accessing the operand, the contents of this register are automatically incremented to the point to the next consecutive memory location, or we can say automatically incremented to point to the next item in a list. For example, we have R1 plus. The content of register R1 are used as an effective address, and after the operand is accessed, this content are to be incremented. So next one, auto decrement addressing mode. Auto decrement mode is like register deferred mode and like auto increment mode. In that at runtime the address of an operand is contained in a register. However, with auto decrement mode, the contents of the register is decremented each time the instruction is executed. The contents of a register specified in the instruction are first automatically decremented and are then used as the effective address of operand. For example, minus R1. The content of register R1 are to be decremented before being used as effective address. Hope you understand this auto decrement addressing mode also. And let's move on to the next slide. So here we have problems on instructions. So the problem is registers R1 and R2 of a computer contains value 1200 and 2400 respectively. Now we have to find the EA of the memory operand in each of the following instructions. So we have the instruction 5 instruction, I think 4. We have the 4 instructions. We have to the memory operand for this. So first instruction is load 20 R1 R5. Now, as we all know, given in the question, 1200 R1 is 1200 plus and 20 is the instruction. So 1200 plus 20 will be 1220. So we are loading that R1 to the R5. Now next instruction, add minus R2 comma R5. As you all know, R2 is 2400 as given in the question. So 2400 minus 1. We are loading that. We are adding that R2 to the R5. So now we will get the 2399. Now third instruction is move hash 3000 to R5. We are just moving the 3000 to the R5. There is nothing else. It is very easy if you understand the instruction. So we are moving the 3000 to R5. Then the effective address will be 3000. Then fourth instruction is R1 subtract R1 plus comma R5. R1 is 1200. We are subtracting to R5. So effective address will be 1200. Hope you understand this problem. Anyone have any doubt? Any doubt? So no doubts. Okay, let's move on to the next slide. So second problem is registers R1 and R2 of computer contain 1200 and 4600. What is the EA of the memory operand in each of the following instructions? So let's solve this problem together. Before that, you solve by yourself and let me know the answers. Solve by yourself and let me know the answers for this. Okay. Okay, let's see the answer for this. First instruction is load 20 of R1 comma R5. So we are adding R5, R1 is 1200 to the R5. So as like this problem, we are adding 1200 to the R1. So sorry, R5. So as like this, we are adding 1200 plus 20 will be the answer. Effective address. So next B instruction, add minus R2 comma R5. So now 4600 minus 1 will be the answer. So here, let's see the advantages of addressing modes, what we have just seen in detail. It provides larger address space, usually up to several GBs, provides larger address space, usually up to several GBs, supports relocality of program from one memory block to another. Some systems have special base register and others permit the use of general purpose registers. It gives programmers facilities such as pointers, counters for loop controls, indexing of data, and program relocation. Reduces the number of bits in addressing field of the instruction. So, do anyone have doubts? So, hope you understand this session. If you have any doubts, please let me know now so that I'll be glad to clarify you. So, no doubts. Hope you have enjoyed this session today, and thank you all. We'll meet in the next class.